Back in 1905, when Albert Einstein concluded that the speed of light is constant, he realized that that had a profound impact on the passage of time. He found that, for instance, if I'm looking at my wristwatch and there's another wristwatch that is zipping by, if I carefully compare the rate at which time elapses on my watch and the moving watch, I'll find that time elapses slower on the moving watch compared to my own. Time in motion, in that sense, slows down. Now, how do you come to that kind of wild conclusion? Well, you need to be Einstein, obviously, but we can follow in Einstein's footsteps. And to do so, we need to have a clock to measure how quickly time elapses. Now, you could use, in principle, any clock at all. A Rolex watch, a grandfather clock, I don't care anything. It will all give the same answer. But there's a particularly useful clock that makes the analysis transparent, simple, easy for us to figure out how motion affects the passage of time. It's an unfamiliar clock. It's called the light clock, and it consists of two mirrors facing one another and a ball of light that bounces up and down between them. So you can think of this as going tick-tock, tick-tock. And every time it goes tick-tock, the counter goes up by one, so it captures the amount of elapsed time, the number of tick-tocks that have gone by. Now, what I want to do is I want to compare how time elapses on a stationary light clock compared to a light clock in motion. So just imagine that I've got a light clock right here, and I'm on a train zipping by in that direction compared to you. Now, from my perspective, of course, it's all of you guys that are rushing by in that direction. So as I look at my light clock, I do not notice anything unusual at all. It's just going tick-tock, tick-tock from my perspective. From your perspective, the interesting thing is, if you follow the trajectory of the ball of light in my clock, what will you see? Well, the ball of light starts here, and then it travels up to the upper mirror in this location. So it goes along a diagonal trajectory, and then it continues on to hit the lower mirror further down the track, another diagonal trajectory. So from your perspective, the ball of light in my light clock is going tick-tock, a double diagonal trajectory. And the fact is, that trajectory is longer than the straight up and down trajectory that your ball of light is going up and down in your light clock. And that, taken with the speed of light being constant, is why time slows. Now let me show you how all that goes. So let me have two of these light clocks, put them next to each other, and let's set this guy in motion. And look at the trajectory of the ball of light. It's diagonal down and up, diagonal down and up. And because the speed of light is constant, but this diagonal trajectory is longer than the straight up and down trajectory, time elapses more slowly on the moving clock compared to the stationary one. Now let me just break this up into a couple pieces so we can see this a little more clearly. So again, put them next to each other, set this clock in motion, and notice that this clock has already reached 1. This one is still at 0 because this ball of light has had to go all the way down and all the way up, and because that trajectory is longer than the straight up and down, but the speed of light is constant, it hasn't yet had enough time to reach the upper mirror. So it still reads 0. And we can carry on in exactly the same pattern. The ball of light going on the double diagonal, this one has already reached 2, this one is still at 1, and by the time this one has now reached 3, this one is only at 2. So time in motion, in this sense, from our perspective, looking at that moving clock, time is slowing down. And it all comes from the speed of light being constant, because the longer trajectory at the same speed means it takes longer for the ball of light in the moving light clock to go tick-tock. Time slows on the moving clock. And let me just emphasize, this has nothing to do with some weird feature of light clocks. This would be true for any clock at all. The light clock simply makes it manifest, obvious, clear, simple for us to figure it out. But use any clock that you like and the result will be the same. Time in motion slows down, and it's everything. If you were watching me in motion at very high speed, I would look like I am in slow motion. We don't know about this because the effect is only significant at high speeds, near the speed of light. But the bottom line is, Einstein established that time in motion slows.